Hi, good morning, everybody. I'm Jeff Mendelsohn. I'll be the speaker for this talk. Surprise. I'm from Bloomberg. I'm a team lead in perhaps the best software infrastructure group at Bloomberg. I do have a request for everyone. Actually, I have a couple of requests. The first is that my boss is here today, so I expect a lot of applause at the end, whether you liked it or not. Thank you. The second is this talk in dry runs, half the time I get a lot of feedback, a lot of questions during the talk, and we end at the right time. If I don't get a lot of feedback, a lot of interruptions, we're going to end early. I apologize if that's the case. Plus, I get nervous, like everyone's falling asleep on me, and I start talking faster. It doesn't go well. Today's talk will be on reader-writer locks, specifically in comparison to a mutex. In other words, using a mutex in place of a reader-writer lock, which is surprisingly good. Just to make sure we're all talking about the same terms, the same items. A mutex is something which provides a thread single ownership of something, like access to a data structure. Classic example from C++11 is standard mutex. A reader-writer lock is a bit different. It allows either one person to have exclusive access, one writer, or multiple readers to have access and work concurrently. Sorry, is there a question? No, okay. So therefore, when we have multiple readers going through, we expect higher concurrency, we expect to get more work done in the same amount of time, we expect good things. That's why we use them. Reader-writer locks can have a read or a write preference or can actually be unspecified, but let's stick with read and write. A read preferring reader-writer lock allows, when a reader currently has the lock, new readers to come in and join him. And this is great. It gives you actually better concurrency. The problem is you can starve out your writers. A writer preferring lock doesn't allow that. It doesn't allow writers to starve out readers, but it prevents readers from starving out writers. At least those are the terms I'm going to use. And the classic example from C++17, at least standard shared mutex. Moving on. So there's a rumor, there's a belief, there's a meme, I'm sure, that apparently mutex is all we need. That mutex works in place of shared mutex or whatever other reader-writer lock you have just fine. And the argument kind of goes like this. Well, a reader-writer lock does more. It allows you more flexibility, therefore it must have more overhead. And that's true. Right? To get this extra flexibility, you have to do additional work. Your hold times for a lock, regardless of what your purpose is, as a good programmer, should be very short. And this combination, this short hold time and this additional overhead, leads to the conclusion that if the overhead is greater than the additional concurrency, that mutexes are better in all cases. This is not true. It's not better in all cases. But in a lot of common cases, in a lot of cases where you wouldn't expect that to be the situation, it is true, surprisingly. There's a lot of circumstantial support for this as well. At Bloomberg, we have a lot of chat groups. This comes up pretty frequently. If you do internet searches, you'll find either this statement exactly, use a mutex instead of a reader-writer lock, or statements which imply this. And as it turns out, it's pretty easy to verify yourself. It's not such a rare situation, which again was, at the time, something I didn't believe. So I got into a weird situation, which is what started this whole line of research and ended up with me losing a lunch. A little embarrassing. I had a teammate who was working on a map-like component. And it was supposed to be a lot of readers going through this component and accessing data and an occasional writer. Situation where you'd expect a reader-writer lock to be what you wanted to use. And he said to me, Jeff, I'm going to benchmark this. I'm going to benchmark it with a reader-writer lock, and just for safety, I'm going to do a mutex. And I'm like, no, you're wasting your time. But he's like, no, I'm going to do it. And he did it. And he showed, hey, the mutex is working a lot better than the reader-writer lock for this component. And I'm like, well, no, you did something wrong. Let me look at your code. I went through the guy's code, looked fine. So I convinced myself, well, his benchmark must be wrong then. It must be measuring something ridiculous. So we looked through that, and of course, it wasn't what I would have done, but it wasn't bad. So now I was getting a little nervous, a little concerned. And I was left thinking, what could possibly be wrong? How could this possibly be the case? So I looked at the reader-writer lock itself, and this is where badness started. Our implementation that we were using was based on atomics, but from looking at it, it looked like it was doing 3 to 5 times as much work as it had to be doing. So surely that inefficiency was why Mutex was beating our reader-writer lock, for sure. And I'm a New Yorker, I'm a little loud, I'm a little boisterous. And a guy who sits behind me said, well, I'll bet you you can't outperform the Mutex for this case. I'm like, well, how could you possibly know this? You just came into the conversation. This is a safe bet for me. He's a very particular person, so he actually typed out the bet. It was like 2 pages of text. It focused on using the Linux system, doing workload appropriate to this component. it seemed like things which I was already convinced were wrong. So it seemed like a very safe bet to me. In fact, it seemed so safe, I upped the ante and I said, you know what? I have an intern coming. I'm going to have an intern write this reader-writer lock to the specification, and we're going to kick your butt. And he's like, fine. And he said, and he came back to me, equally as confident. You know what? I'll even give you 2 months after the intern leaves to fix his work, so to speak, to make sure you got a fair chance on this bet. And I'm like, perfect. So the intern came in. He did a fabulous job, gave me exactly what I was looking for, better, cleaner code than I expected. And I thought this was done. I thought this was an easy win. Unfortunately, not so much. Even though this lock was much more efficient, even though it ran a lot faster than our original implementation, it still wasn't competing with the Mutex where I thought it should be. 2 months go by, I still hadn't figured it out, so I lost the bet. Took him to lunch. I tricked him, of course, got him to go to my favorite restaurant. That's how that ended. But while I lost the bet, I was still very emotionally attached to this problem. So I wanted to look at it further, and I started with the benchmark. So I'm going to describe the benchmark I built, and if you have questions as to why I did something a certain way, please interrupt. Let's focus from a threads point of view. So there's going to be lots of threads coming through. A thread's going to come into something which simulates a shared data structure. It's going to take the next work item, so to speak, a job. The job will be marked as either a read job or a write job. So it'll take the appropriate lock. For a read job, it'll take a shared lock. For a write job, it'll take the exclusive lock. It'll do some work. This work will be a busy wait. That'll be affected by some load factor. This load factor will range from 1 to 10,000, 100 being about the size of the amount of work we did in the bet, how much this map by component was doing. It turns out to be about 300 math operations is the 100 value. About 150 adds, 150 multiplies. And then it would unlock appropriately. Stepping back to how the system which controls the thread works, I'm going to have one thread which comes in, and it's going to set an atomic variable saying go. All the threads doing work will be waiting on that, waiting for that signal. It'll then sleep. All the threads will do their work. And then it'll say stop, and then it will join with all the threads. Then I'll measure the actual time took. So I slept for some predicted amount of time. Of course, it's going to be different. So I take the actual time. I scale the amount of work by that. So I have jobs per second. I'm going to repeat that a large number of times. And then I'm going to take the 80th. I tried to munch 2 words. That was good. 80th in order. Take the 80th percentile value on the high side, 80% closer to the max, as an order statistic for this problem. The code for this, for the intern's implementation, and for my eventual implementation is available at that GitHub location. Any pictures? No? Moving on. See, this is the case where I'm not getting a lot of questions. This is concerning me. I ran this benchmark on a lot of platforms, a lot of compilers. The only obvious hole in what I ran this on is on Windows. I didn't have access to a Windows box. I'm sorry. I ran these results. All of the results are pretty much identical to the results I'm going to show you for the Linux box. There are 2 exceptions to that, which are Sun and Darwin, so I'll give some results on those as well to show how they're different. This is the specifications for the box. They're all, well, except for the Darwin box, they're all shared boxes. I apologize for that. I woke up very early in the morning to produce these slides for you. I woke up at 3 o'clock, ran to about 6. I had to do that 3 times for the production, a couple times to try it. So I hope I worked hard enough for you. This is the best I could do, and I think it's clear enough win that it's not a question. I do want to take a moment to manage your expectations here. I have way too many graphs in this talk. It's a lot less than it used to be. My wife had to sit through a 4-hour version of this. Very kind of her. I reduced that 4 hours by focusing on Linux primarily, since they're all basically the same. And I'm going to be showing that synchronization is very expensive. Anytime you do even one atomic write operation, you've taken a big hit to what you could potentially be doing on your machine. However, I'm looking at one sort of dark corner where you have, let's say, 16 threads continuously hitting a lock all the time. Hopefully that's not your system. Hopefully 1 or 2 threads at the most are going to that lock at the same time. So this is sort of a dark corner. This is sort of a bad case. So don't become overly depressed from what I'm showing you. I'm hoping this isn't your usage pattern. We'll go through the losing implementation. We'll go through the implementation we came up with at the end. I will be confirming that Mutex is great when you have a lot of contention, a lot of threads going for the same lock at the same time. There's no way about that. But in the end, I'll show you a lock which has a small loss when we should have been using a mutex, and a great win when we should be using a reader-writer lock over a mutex. Having said that, it won't be a great win in the absolute sense that we have a lot of scalability. It'll just be a great win relative to mutex. So let's start with the cost of one atomic. I've already hinted that it's perhaps more than we think. So I'm going to use my benchmark for these results as described. I'm going to simulate the lock. I'm going to create something called a no lock, which does nothing. So obviously it's not a lock. It's just it does nothing on the unlock and lock commands and nothing on the lock shared and unlock shared commands. And then we'll also have an atomic version, which for the simulating the right side, it'll do a fetch add, both in the unlock and the lock. And it'll use acquire release semantics. And the shared will just do a load. It'll be on the same memory location. So if I have readers and writers, they will interfere, even though this isn't the lock. Is that clear? No, it's not an actual lock, so it's just one fetch add or one load, and if the only contention would be on the cache lines themselves moving between the cores. Very good. So this is what my graphs will look like. On the left-hand side, we'll have jobs per second. On the bottom, we'll have number of threads. So jobs per second for threads, we'll start them all. I'll then describe the scenario. It'll be 100% read in this case. All readers, all the work jobs are readers. The threads aren't labeled, the work is labeled. And the load is 10,000, which again is 100 times what this bet from the map-like component was. It's about 30,000 math operations. Then, of course, I'll have the lines. Here I have atomic versus null. Okay. So it shows they're basically the same. Good. Which is expected because we have a very long hold time. So basically the lock comes in, does what it's going to do, in this case not really a lock, and then there's a very large operation. So the percentage of time on the lock is nothing. We'd really expect the overhead for doing nothing versus atomic to be 0. And that's basically what we're showing here. So this graph is showing nothing, which is good. Actually, it is showing one thing, though. It's showing the kind of behavior we want when we do multi-threading behavior. As I add threads, I get more work done. That's a good thing. That's scalability. We're going to lose that very quickly. So just to sort of show the progression, we're going to move to 90% reads. This is now doing some writes and some reads. When you do atomic operations, since now it's to move the cache line between the cores, and that can slow it down substantially. However, since we're still at that ridiculously high load, we don't see that effect very well. Moving down to all writes, again, we still don't see the effect because the workload is so very high. So again, these 3 graphs show a very long hold time. The next 3 will show a short hold time. And we'll see the effects of the actual atomic operation. So again, on an all-read workload, with a short hold time, about a tenth that in the bed, about 30 math operations, we see the performance of the atomic lagging behind. Doing an atomic read versus doing nothing now has an apparent cost. About 20% at the extreme. But it's still scaling nicely. It still, as I add threads, I get more work done. When I move to the 90% read, so again, this is just a very small percentage of writers, the effects of having to synchronize the cache between the cores becomes very apparent, and I lose all scalability. So again, atomic is the blue line here, and after about 6 or 7, well, after about 5, I guess, threads, I'm not able to get more work done by adding more threads. That's really not what we wanted here. This is sort of the main argument for why the mutex is going to do so well. Is that we really can't do better. Even just one atomic operation is going to make us lose our scalability. And of course, doing nothing is just as scalable as always. Yep.
Because you like interruptions. So just to repeat that so I understand, that's just essentially just the cost of the CPU pushing those writes through to all caches, which destroys the scalability here.
Yes.
Okay.
Doing the atomic write invalidates the cache line. It means it has to be reloaded on all the cores. I didn't test whether having more cores makes that worse in some sense, because I guess it could. But on this box, this is the results I got. Does that explain that?
Yeah.
Is it surprising?
It is. It is.
I thought so too. It blew me away, to be honest. Of course, I didn't do this work in this order. So I kind of, you hit a problem, then you back up, you say, what the hell is going on? You come back and, oh, this is what sort of explained it to me at the end. So this should really be the last slide. Any other? Oh, sorry, go ahead.
Is this caused by fault sharing?
No and yes. I mean, I can see why you associate it. It's not false sharing here because I don't have two things where I want one or the other. It's I have one thing where I want it, but it's the same principle, that memory has to move to other cores.
It's true sharing.
It's true. Is that a word?
No.
I like that. It's true sharing, yeah. Anything else? Thank you. Oh, wait, I should have put the decks of cards. That's what you've done, the Bloomberg cards and given them out. All right. Moving along. So just for completing these set of graphs to match the previous ones, this is all rights. And yes, the amount of work we're getting done is a little bit less, but that's not the key takeaway in my mind. The key takeaway is that it's still unscalable. So let's move to something a little more interesting. Let's look at mutexes and semaphores on this platform. So we'll start the very long hold time again, and with 90% reads. Now here again, a mutex and a semaphore allow only one thread. I apologize, I didn't say what I meant by a semaphore. A mutex allows one thread to, a semaphore allows some counted number. Here I'm using a count of 1. So essentially it's mimicking a mutex. Okay, so we have the atomic line, which scales nicely, and the mutex and the semaphore, which allow only one thread through at a time. Of course, you get no extra performance for no extra threads. You'll have to wait for the mutex. So that's as expected. The performance difference is interesting. Now let's move to a very short hold time. Still mostly reads. Not that it matters, because again, we're looking at the mutex and the semaphore, but it changes the performance of the atomic, as we saw before. And we see that a mutex and a semaphore are both much more expensive than this atomic lock we discussed, this fake-it lock. The amount of jobs done per second is way down. None of them are scalable, and it's all as it is. So to recap, the mutex performs much worse than a single atomic operation. The single atomic operation performs much worse than doing nothing. We're already in a deep, dark, bad place. Now we're going to talk about locks relative to mutexes and see how much worse or better they can be. Let me step back for a moment. There's some concerns when you design a new lock that you should have. One is the fairness of the lock. And that can mean a couple of different things. For reader-writer locks, it primarily references, should it be reader preferring or writer preferring? I'm only going to consider writer preferring locks. I don't want the scenario where readers can starve out writers. That was a choice I made. I will compare it to a lock that is the opposite. The pthreads lock by default is reader preferring. I'll show that it didn't affect the performance in any way. But for use at Bloomberg, we wanted to have writer preferring locks. What do you do when you can't get the lock? Do you spin? We will not allow that. We will require the threads to be unscheduled or descheduled. Unscheduled, descheduled? You're nodding. You acted like you knew what I was talking about. Okay, descheduled it is. Again, at Bloomberg, we'd run lots of things. Not again. At Bloomberg, we'd run multiple things on each box. If a thread was busy waiting, it's just wasting CPU cycle, something else could have been running there on. It's just really not in our setup to busy wait. Also, in some tests for busy waiting, you can get some really bad behavior out of that if you're not careful. I don't know, are people familiar with like Tidex locks or anything? Locks that order threads that are coming in? You can get some really, really bad behavior out of that. We didn't want to start down that path. Another major concern is priority inversion. For example, let's say a very low priority thread gets a lock. It now goes along doing its work at a very slow pace. And all these high priority threads are waiting on that lock to do their work, and they can't. This is not good. This actually led to some major failures in systems in the past, but I didn't bother looking them up. I apologize. One common solution to that is when you have a mutex and a thread acquires the mutex, it inherits the priority of the highest of all the threads waiting on the mutex in itself. So by definition, you can't have priority inversion. There is no slow thread in that case. It just moves up to the highest priority. And I want whatever lock we design to have real usage scenarios. While there are real work problems where you have one write per 10 million reads, it's not a general case. I didn't want to design for that. Any questions? No. Okay. So let's talk about the implementation my intern developed, which was fantastic. Yes, sir.
I really have a question. I have heard from our... Wait. I've heard from my boss, Andre. Hi, Andre. that spin locks sometimes do improve things if they spin for a very short time.
Yes, to spin once or twice or 4 times is something we do at Bloomberg. We do it where you expect to obtain the lock quickly. If you're not sure how long you'd be spinning for, we're avoiding it.
Okay, I just wanted to make sure that we
yes.
didn't tell people that spin
No,
locks were
spinning in
evil.
general, retrying is not bad in general. Indefinitely spinning can be bad in general. Thank you. Okay. Where was I? So the intern built this lock. It had minimal overhead. There's as few atomic operations as possible. It's very tight, beautiful code. A couple of cast loops, or 1 or 2 cast loops for every method. Excuse me, cast is compare and swap. Everyone, okay, it's an atomic operation where you're testing and change. Okay. It is writer preferring. So what it actually does is, if there's a pending writer, excuse me, new readers will pend themselves and join something, as opposed to moving forward. And when a writer unlocks, it prefers to give the lock over to the group of readers that are pending. So it sort of flip-flops between read access and write access. And we use a primitive, a semaphore, to handle who gets the lock next of the set of readers that are pending or the set of writers that are pending.
So what happens when a writer is waiting when your writer unlocks?
So what happens when a writer is waiting when the writer unlocks? I'll get into this again later, but just answer it now. When a writer unlocks, it's going to hand off to readers first, and then the readers are going to hand back off to a writer if they can. If there are no pending readers, it'll hand off immediately to the next writer.
Are you queuing then the readers that come after the writer that's pending?
Readers that come after it? No. Okay. So the question was, do I stack the pending readers a writer, pending readers writer, pending readers? No, it's just one group, and all the pending writers. Okay. And by using these semaphores, we get whatever the default priority inversion is for the system and whatever the default fairness is for that primitive, we inherit that. So in more detail, the atomic state tracks the number of readers, the number of active readers in the lock, the number of pending readers, the number of readers who are waiting for the current writer to finish, and the number of writers, both active and pending, put together. There are 2 semaphores, one to block pending readers, one to block pending writers. And so there's 4 methods I want to talk about. I wish I could have shown the code. The code, gives you all the detail, but it's a lot of atomic operations and comparison swaps, and it seems like pseudocode was better for that. Also, it wouldn't fit on slides, is what I'm trying to say. So the lock operation, first, the writer comes in, he increases the number of writers. When I say that, I occasionally use the word then here, but it's all atomic. It's all done at one shot. So he increases the count of writers, and after any readers or other writers, he waits on the write semaphore. On the unlock side, our thread that's releasing the write lock will decrement the count of writers, and since there are no active writers, we'll take all the count of the number of pending readers. Excuse me, let me try that again. Since I have the write lock, there are no active readers. There are potentially pending readers, so I'm going to move those pending readers over to active readers in the atomic state first. And here, it truly is a first and a then. And then I will post to that semaphore blocking those readers, that count, to let them through. And there's no possibility of a mistake or a race condition here. If there are no pending readers, I'm instead going to hand off to a writer if there is one, which comes back to your question from earlier. Is that reasonably clear? Good. On the shared side, it turned out it was important to have a atomic level, to look at this atomic state and do a short circuit, to skip having, I'm sorry, I'm ahead of myself. I backed it up. So he comes in, he looks at the atomic state variable. If there's no writers, he increases the count of active readers. He goes right into the lock. He goes right into owning the shared lock. If there are, he increases the count of pending readers. Excuse me, if there are writers, he increases the count of pending readers and waits on a read semaphore. And to unlock, he decrements the count of readers. And if he's sort of the last guy in the bar, he closes the door. If he's the last reader and there is a writer, he's going to post to the write semaphore. The readers before him who exit don't need to do that and shouldn't do that. All right, so if there's no questions, I'll move into his performance. Good. So again, it's the same type of graph. Jobs per second versus number of threads. The scenario is this is all reads, and the load is ridiculously high. I'm going to be showing some additional lines on these graphs. So to focus on the 2, or to provide focus for the 2 I want to talk about, the Mutex, the blue one, will have its arrow, And the implementation we're talking about, in this case, the intern's implementation, will have the other arrow. And then for clarity, whether this is a good or a bad scenario for the lock relative to a mutex, we'll have a smiley face or a sad face. In this scenario, which again was ridiculously long hold time and 100% read, where a reader-write lock should be king, it was. And that's good. It was scale. Oops.
What's speed thread? Is speed thread just a semaphore?
I apologize. Thank you. So the question is, what is the p thread on this graph? I wanted to show some other reader-writer locks on these graphs as I go through, specifically p threads, implementation of the reader-writer lock. By default, that is set up as a reader-preferring lock, which supposedly gives it better performance. It can starve out writers. That's okay here. We just wanted to see what the performance was. And we showed that we're outperforming the standard p-thread implementation that came with this box and compiler. And I say box and compiler, all the boxes and all the compilers are pretty much the same. So again, I'm going to be a little pedantic here. Moving the load down by a factor of 10, we still see the behavior you're looking for. The lock we're comparing is still scalable. Of course, a mutex is never scalable. And the performance is much higher than the mutex, so we're still good here. And moving down to the low of the bet, we're still good, right? Our new implementation, the intern's implementation, is still substantially more performant than the mutex. But here's where we start to see the difference, is it's no longer scalable. Even at a reasonably practical hold time, adding more threads will not get us more work done. It's a bottleneck. It's a problem. Yes?
Just mention this again, the cache coherence issue.
I can't say that for a fact, but yes, my belief is that the atomic operations reduce scalability. I know these have to do something similar to that, therefore I'm implying that that is the case. But I can't say it for a clear fact. Is that a fair answer? I'm sorry, I had to repeat the question. The question was, again, this is due to the cache coherency between the cores for an atomic operation. Okay, I apologize. That's the best answer I can give. Yes, I believe that's the case. I mean, I full-heartedly believe that's the case. I haven't proven it. Yes?
Could you explain the units on the graph for me?
Yes, it's jobs per second versus number of threads. So the left-hand side is jobs per second. Is the number of threads. Good? Good. I changed it since the last time you saw it. Okay, so let's move into still 100% reads, now a very short hold time, still outperforming, still bad scalability. We're better off running one thread than multiple. We'll go down to the ridiculous, something like 3 math operations. We see the mutex and this reader-writer lock are performing about the same, even though it's all read work. Okay, so recap so far. On exclusive reading, this implementation did pretty well. It crushed mutex when the hold times were very long, as you would expect, and it did what we want except for the scalability. So let's mix the workload a bit. Let's move to 90% readers, 10% writers. Did I say that right? 90% readers, 10% writers. Again, at the ridiculously long hold time, we see this reader-write outperforming the mutex very nicely, but there's no scalability now, even at 90%. Part of the reason I believe this is due to the atomic operations or the effect of the cache is because it happens at the same place. Right? As soon as I go to 90%, I see basically the same flattening. So there's a lot of circumstantial evidence for that.
Verification?
Yes?
So when you say 90% read, that means that of the things that are happening, 90% of the things that are happening are read operations, 10% are what? What does the load mean?
The load is how much work is doing relative to the bet. A load of 100 was basically the same size as the bet, about 300 math operations. 10,000 is about 30,000 math operations. 15,000 adds and about 15,000 multiplies. It's just a fictitious busy weight.
Per what unit? Per second?
No, per job.
Oh, the job. Okay, per job. All right.
So sorry to reiterate on that. Is when you say 10% write, is it a job that's only doing writing, or a job as 10% instructions that are writes?
So the benchmark is set up very fictitiously. You take a job. That job is either read or write. It's not a queue of jobs. It's just, this is the index, do some math, figure out what job it is. And all the threads start different offsets. So there's no interaction between the threads to get this. But yeah, job is either marked read or write. It does the same amount of busy waiting regardless of whether it's read or write. It's just which lock does it acquire? Does it acquire the read side or the write side? Okay. Moving along. Still to 90% read, reduce the amount of work done per job. And we see now that the mutex and the reader-writer lock are performing about the same. This is concerning, right? The amount of work we're doing, the overhead for the lock is obviously a lot higher than we think it is, or at least in combination with the lack of scalability. And moving down to the workload of the bed itself, and this is why I lost, we see we're significantly underperforming the mutex, even at a very highly biased workload. And moving down to the short hold time, it just gets worse for us. And moving down to the ridiculous, it's the same story. So to recap the 90% reads, Mutex was generally better. It's really all I can say. Only with very long hold times did the reader-writer lock outperform the Mutex, which is not what I expected, which is why I lost the bet, and which is what made me very unhappy. So let's regroup for a second. Let's think of what we want to do. I lost the bet in comparison to Mutex, so I took that very personally. So my goal was to beat Mutex. My goal wasn't to produce the world's best reader-writer lock. My goal was just to move, to have a lock which, when we expect a reader-writer lock to outperform, it does. And when it's not going to beat the Mutex, it's only going to lose by a little bit. And again, I want to crush the Mutex when I have really long hold times, because of the scalability. I should be able to scale it in general. Is there a question? No. Okay. So let's discuss this implementation a little bit. Again, while not a fact, a belief I developed along this process was that the reason a mutex is working so efficiently is that it allows you to reacquire itself. In other words, if a thread comes in, acquires the lock, releases the lock, and then immediately comes back to reacquire it, it'll generally get it again. In fact, unless it's run out of its time slice, it almost definitely will get it again. And again, not known as a fact, but through some experimentation, that's the working hypothesis, is that the reacquisition is what makes the mutex so efficient. So I'm going to build something which is basically a modified mutex. It'll be a mutex in general with some extra bookmarking or accounting to keep track of the readers. As such, it won't have an explicit preference for readers or writers. In other words, a writer can't hand off to a reader because that would imply a problem with the reacquisition. I'll try that again a little bit. This next line on my slide, unfortunately, is a little outdated. I figured out what was going on there, and it's not a problem. I did an experiment where I wanted to, since the lock wasn't designed to be explicitly reader preferring or writer preferring, I wanted to see if there was some bias in the lock for who got the next lock. Was it a writer? Was it a reader? My thought being, of course, that this is ridiculous. This is just a sanity check. But I ran it with 50% reader, or the jobs being 50% read jobs, 50% write jobs. And I found out that the writers were actually getting the lock like over 60% of the time. That was a mistake. It was actually they were acquiring the mutex over 60% of the time. There's a short circuit around the mutex in the code, and if you account for that, you do the probability math, it works out exactly right. Everyone's getting the lock. Everyone's acquiring the mutex fairly, which is good because we have faith in Linux. And I wanted to use a primitive, in this case a mutex, to select the next reader or writer to, again, obtain all that priority inversion protection and the fairness of selection of who the next thread is. Okay. So the implementation has an atomic state that tracks the number of active readers, the number of pending writers, and whether there is currently an active writer. It's kind of sort of the reverse of the previous case. There's one mutex which does the majority of the synchronization. Basically, every thread which comes in to get the lock, unless it has some short circuit, is going to acquire this mutex. And there's a second primitive for when a writer acquires the mutex and it has to wait for the readers to complete. It'll wait in a semaphore. Okay. A little more detail. Oh, I'm sorry, one more thing. Since the writer's path potentially has to go through two synchronization primitives, there's some performance concern there. So we want to check the scenarios where there's a low read workload, a 10% read workload, for example. So when a writer comes in, he's going to increase the count of pending readers. He does this just atomically. It's not a cast loop. He locks the mutex, giving himself full access to the lock. And then he decreases the count of pending writers and notes that there is one active writer. However, he's not ready to go do his work yet. He has to wait for all the readers to drain out of the lock. So if there aren't any readers, he's going to wait on a semaphore, and when the readers are done, they'll tell him. They'll close the door behind him as they leave the room. On the unlock side, the writer will come in, he'll erase the fact that there is a writer, and then he'll unlock the mutex, allowing other people to acquire the mutex. Pretty straightforward, I hope. On the lock shared side, on the reader side, we'll do a short circuit first. If there's no readers or pending if there's no pending writers or active writers, we're just going to increment the number of readers and attain the lock. That's proved to be an important optimization for this lock to outperform mutex on some platforms. Well, if that's not the case, we'll instead lock the mutex. So basically everyone without this optimization is going to lock the mutex first. Increment the count of readers, and then unlock the mutex, allowing other readers to come in immediately if they can get access to the lock. On the unlock side, we'll decrement the count of readers, and if this is the last reader and there is a writer, we'll tell the writer you can go ahead. We'll close the door behind us as we leave. Looking at performance, again, we're showing jars per second on the left and number of threads on the bottom. We're going to compare the mutex, which is the blue line and has the highlight, versus this reader-writer lock, which is that magenta line with the other arrow and the happy face for beating the mutex. We're also going to compare it to the p-thread implementation of the reader-writer lock and the intern, the implementation we were talking about before. Unfortunately, both the losing and the reader-writer lock are the same line on this graph. At a ridiculously high hold time and all read work, we get the results we're expecting. Very scalable, and we're outperforming mutex dramatically. Scaling back the workload to a long hold time, basically the same outcome. Scalable, outperforming mutex handling.
Can you say what you just changed again? I didn't get it. What did you do?
So from here, which is an extremely long load, extremely long hold time for the lock, we decrease the hold by a factor of 10. Reduce the load by a factor of 10.
So hold and load is the same thing?
Yes.
Okay.
It's what we're doing in a busy. I apologize for not repeating the question again. I feel so bad. So again, moving on to the workload of the bet, about 300 math operations of hold time, all readers. We lose all scalability again. We're still outperforming the mutex, so from this point in my life forward, that's a good thing. We're still beating mutex. At short hold times, we're still beating mutex, again, for all read workload. Again, good. And at ridiculously low hold times, 3 math operations, we're basically tying the mutex, so we're indifferent. So to recap, the new implementation did very well on 100% read workloads, and it really crushed the mutex on the very long hold times as we wanted. So moving down to the more interesting work, where we have 90% reads and 10% writes. We see no scalability again, even at the longest hold time. We are outperforming mutex, where the magenta line. However, and this is, I don't know what the right word is, interesting. The other implementation is outperforming us. The losing implementation is outperforming us on this particular workload. From that and from some research which followed, the key takeaway from this talk, I think, isn't that this is a great new best reader-writer lock, it's that this fits a different workload better than the current shared mutex and the current mutex. There are other possible implementations out there which might be good as well. In any case, this is us beating mutex, so we're happy. This graph is odd. Normally we see in the graphs, a shifting, a changing, which is smooth. This one is just different. Again, I ran this on a shared box, so my presumption is somebody else was up at 4 o'clock in the morning and did decide to do something. I don't know that for a fact. However, these are valid results. This is the results we took. It may not match the presumptions we're showing, but this is the outcome. And whatever happened here, we tied mutex, so it can't be bad. So moving the load down to the size of the bet, again at 90% reads, we see we're outperforming mutex still. Again, all good. Going down to very short hold times, still beating mutex. Not much to say here, except that mutex is beating both p-threads and the previous implementation, as we already saw. So let's move down to the ridiculously short hold times. And let's recap the 90% read workload. Basically, we performed exactly as desired. We beat the mutex, I believe, on every side except for one where we tied. So we're doing very well on the read workload, whereas before we weren't. On 90% reads, we were losing to mutex. Let's go ahead and look at the extreme. Let's look at all write workloads, places where we expect Mutex to beat us. At the ridiculously long hold time when we're doing all writes, basically everything goes through sequentially, right? There's no availability of parallelism. The numbers on the left are a lot smaller than they were in all of the graphs. Basically, this is rounding error is the only difference you see here between 16 and 17, because I only reported integers. Basically, everything does the same because the workload is taking so long and there's no opportunity for concurrency. Reducing to a very long hold time, we see the Mutex and the new implementation doing basically the same and handily outperforming the other algorithms. Again, on all writes where we expect Mutex to be best, we see us basically tying Mutex again. This is at the workload of the bet. Moving even shorter, moving to the 10th the workload, we see us underperforming Mutex by a little bit. But this is where we expect to lose to Mutex. So this is us losing to Mutex by a little bit when we expect Mutex to win, which is what we wanted. And the ridiculously short hold time shows us losing to Mutex, but that's okay. So overall, so far, it looks like the Mutex plus overhead, the new algorithm, is relatively speaking doing very well. And it's giving us great results on this mismatched workload. What I mean by mismatched workload is this is all write work, but I'm using a reader-writer lock. This is where Mutex should have been beating us. Given the overhead of a writer needing to acquire a semaphore in this new algorithm, as we discussed before, it has to go through a Mutex and it may have to go through a semaphore. I was concerned about the performance when there's a small number of readers. So we'll go through the graphs again with the 10% read workload to show that that's not the case. So at a very long hold time for the lock, ridiculously long. Again, we see no real difference between the algorithms. At a long hold time, we show the new algorithm matching Mutex. Moving down to the workload of the bet, we see something interesting. Even with only a 10% read workload, this new implementation is outperforming the Mutex, whereas the other implementation is not, and pthreads is not as performant as we are. At a very short hold time, we're again outperforming Mutex, even with only 10% reads. And at the ridiculously short hold time, we're kind of matching. So let's recap these. So there's no issue with the low read workload is what I'm getting at. Let's recap these 20 scenarios. I phrased this backwards. I don't know why I did that. One time, Mutex significantly outperformed our new algorithm. One time, Mutex slightly outperformed it. 8 times, they kind of tied. 10 times, Mutex significantly lost to this new implementation. Furthermore, if we focus on the scenarios where we want to use a reader-writer lock, the 90 or 100% read workload, there were only 2 times the Mutex matched our new algorithm, and 8 times it greatly underperformed it. So overall, we have to presume this new reader-writer lock is better matched for these work scenarios than a Mutex, which is what we want. So I mentioned earlier there was 2 platforms which had sort of qualitatively and quantitatively different results than Linux. So I want to point out those quickly. I did tests on SUNOS, and having learned my lesson, I started with Mutex and SEMAPHORE, and I showed Mutex outperforms SEMAPHORE and Sun. Yay. Not very interesting. Looking at the locks, we'll focus only on the workload of the size of the bet, about 300 math operations, and we'll reduce the number of slides we're looking at. 90% reads, we see this weird shaped graph on Sun. It's very repeatable. I don't know why it's like that. But we do show, excuse me, this is 100% read. I was looking at the next slide. We do show the reader-writer locks outperforming Mutex here, so fine. Moving to just 90% read, the Mutex outperforms everything, and this is not what we want. This is not what we expected. This is the case, though. I don't know what the conclusion should be here. Should we all boycott Sun? Should we ask Sun to figure out what's going on? Maybe I'm just running on old hardware and old compilers because that's what we have. I don't know. I also ran on this computer, my DARWIN box, and this was the oddest thing at all and took me the longest time to figure out. Fortunately, I eventually realized to compare the Mutex to the SEMAPHORE. On my personal laptop right here, the SEMAPHORE performs better than the Mutex. And again, the SEMAPHORE has just a count of 1. I don't know why it's the case it is. Having seen this, instead of using the Mutex in the implementation, I used the SEMAPHORE in the implementation. So in these results, I'm comparing to a SEMAPHORE as opposed to a Mutex, but that's the most efficient for that type of workload. And we see the behavior we want. At the scale of the bet on the hold times, at 100% reads, we have better performance for the reader-writer locks. And at 90%, we have the same better performance. So in summary, synchronization is very expensive. We started out talking about doing nothing for locking. We showed how doing even just one atomic write is a lot of degradation of performance, and going to a mutex is another step down. So synchronization is very expensive on computers, perhaps more so than people think in general. Oddly, mutex is exceptionally good for this high contention, low hold time work. But we can do better, at least in scenarios where we have some portion of reads in our workload. That's basically all I had, so I hope we have a lot of questions. Thank you. Yes, sir.
It's kind of different domain because it's log-free, but have you considered to compare it against RCU?
Read, copy, update. That's kind of a totally different thing, right? You're
but it's
taking
more or
items,
less
you copy
designed to give priority to readers.
Agreed. And it can be a better algorithm in a lot of scenarios, but it's a different algorithm is what I'm trying to say. They're both fruit, but they're kind of different. Yes, there are definitely places where read, copy, update is king. There are definitely places where it won't be. I don't know where the dividing line is between them, so I have no real good answer for you. Or the simple answer is no, I didn't do that. Yes, please.
I got two questions. First one, really quick. Is this the new default implementation for RW Mutex in BDE?
Oh, the pain. It will be the new implementation for RW Mutex soon, hopefully within days.
And it will be also in the open source BDE version?
It will be in the open source BDE. I will also be putting the other implementation, the interns implementation, in as a variant that will replace what we currently call a reader-writer lock. That's confusing. At Bloomberg, we have lots of these things grown over time. They're all kind of a little different. They all have sort of different functionality. Some have upgrade capabilities for reader-writer locks. So it's kind of become a bit of a jungle, a thicket. But yeah, part of the work I'll be doing once BDE 3.2 goes out is to address these issues, to have an internal presentation on what you should use when and why it's better. And yes, short answer is yes.
The second question is kind of more open-ended. So this kind of situation is very bad because it doesn't scale. And I think I've seen this in our code base multiple times, this kind of contention on reader-writers and stuff like that. So do you have any tips on how we could redesign kind of these paths? What are the alternatives when you have this kind of design?
So yeah, different workloads have different algorithms, like RCU, read, copy, update. Prior life before Bloomberg, or I should say prior life, I'm actually a rehire at Bloomberg, so prior life in between Bloomberg, I worked at trading companies, and there we just set up our systems differently. I reserved a couple of cores to be used by the operating system and the users of the box, which there shouldn't be any. And then the rest of the cores were explicitly assigned to the one running program on that box. That one running program had a thread per core, and only the communication between the cores required any synchronization. So it's a very different running model. At Bloomberg, we have, look, we're running some ridiculous number of things on this box to make sure we keep it running and using electricity to the full ability we can. Whereas at the trading company, it was, well, no, what's the best way to do this in terms of efficiency? I don't care if a thread is busy waiting. I don't care if I need twice as many boxes as I need. It wasn't a constraint. We instead of owning the building where the boxes were housed and having all those constraints, we own one rack in this huge, data center. So yeah, different scenarios will have different things, different architectures, different algorithms. Lock-free can be a very good algorithm or set of algorithms, a very good approach for a lot of these things. But lock-free itself is going to have a similar problem because it still uses an atomic, but it can still be one step up overall in performance. Could be.
So the setup there was a synthetic setup, right? Your benchmark setup that you have. Okay, so just to repeat, what you did you wanted to benchmark the locks, so all the work that you simulated happened while somebody had the lock. So you didn't have all the positives of parallelization, somebody doing work before waiting for the lock. Mm-hmm. So that's why we don't see any gains as soon as you have a writer, right? So as soon as you have a writer here, there was no scalability. Right. You could have done it on a single thread.
Yeah, I'll need your name for picking up the rug I put all the dirt under, but yes. As I kind of said, to clear my conscience, I made this statement earlier. A thread will come in, it'll acquire the lock, it'll busy wait.
Yeah.
It'll immediately release and immediately try to go again.
Yeah.
So yes, that's not typical to most work
Of
scenarios.
course,
You don't
yeah.
immediately come back, and I think that's what you're referring to.
Yes. Okay. Yeah.
Just to clarify, so in all your tests, like you have, like when you set load is like 1,000, the load 10,000. Does it mean like the amount of operations, but in all cases the hold time is the same?
No, I'm
regardless
sorry.
of the load?
The hold time is relevant to how much work you're doing in this busy loop, and that is exactly scaled by the load. 1, 10, 100, 1,000, 10. The scaling is linear, although the numbers I chose are going by factor 10. And 100 being about 300 math operations. Does that answer your question? So the load is always how long you're holding the lock for. It's how much busy looping you're doing.
So when you have a low load, you have a lot of overhead.
Exactly.
High load, you have very low.
And since there's only the two scenarios, either you're trying to get the lock where I'm trying to do busy work, that effectively parameterizes the space. We have the up here.
You say that synchronization is very expensive. I was wondering if it could be atomic synchronization that the compiler is kind of doing behind the scenes versus doing your own synchronization where you're locking a mutex, doing the semaphore yourself. And so I'm wondering if could you compare it to a situation where you're doing mutex in a CV and no atomic operations whatsoever, and see how that compares, where you have total control about what's going on there, and the compiler, because to me when you're doing something atomic, I kind of wonder, well, what's really going on there?
I'm not sure how to answer that question, so let me do my best and see if I get close. For example, a mutex does something different in most implementations, right? It has this direct access to things we as user-level programmers don't have access to. It has, and yes, it's doing something which on Linux is really good. But I chose not to go down to that level, even though you do have access to like mutex and stuff like that. However, the atomic operation comes from more of the silicon than the compiler. And that is, there is a physical statement that the cache lines have to move from one core to another. So I think that is a fair, even though it's done in user space, I think that is a fair statement of what the best you could possibly do is. Because whatever that mutex is doing, it has to do something kind of similar to that at least. I mean, it's not magic. I could be wrong, but I choose to disbelieve in the magic. It is doing something I don't have access to in general. It is doing something very well. That's why I chose to use it at the end. But no, I think there is a true problem with the way the silicon is made that the concurrency can only go so high if you're accessing the same cache line.
I guess what would be interesting would be to actually test that, maybe.
How would you test that?
By using a mutex. So when you're acquiring the lock, you are incrementing the pending, you're incrementing a couple of variables, right? So just using a mutex there to protect that instead of using atomic operations, and then using a condition variable and doing it that way, the old-fashioned way.
Right. I see what you're saying. Okay, I apologize. Let me back up. I did do tests similar to that. Oddly, this is kind of the opposite of fault sharing. When I tried to separate the two into separate cache lines, I did find some confounding of the situation. When I kept everything in the same cache line, so that getting the mutex kind of implied I already had the cache line loaded, essentially it's a free operation to get that write or that read. So I think I did cover that then, if I may hope.
Okay.
All right, maybe not. We'll have to talk later. Yes, sir.
So I can't remember if you showed it at the beginning, but did you compare STD shared mutex with STD mutex?
No, because I didn't have access to a 19 compiler at the time. I have done it since with this algorithm and with another one I'll be talking about some other time. And yes, we're outperforming shared mutex. So perhaps the conclusion to this talk should be not that this is good or better or different or that there's something to worry about here. It's that the people who have implemented shared mutex and like GCC 7 something that I was looking at should perhaps change the benchmarking they're doing, the workload they're considering. Like my belief is they're optimizing for something which is very long hold times or whatever, which is not matching the workload most people or many people are putting through it. So perhaps they could shift their benchmarks to a shorter hold time to more contention, not lose anything, but gain a lot.
Makes sense. I want to know, maybe if someone else in the room knows, if the standard mandates some kind of bias for shared lock. Or for share mutex, sorry. Or if it's like, do whatever you want.
I'll
Because
guess if nobody knows.
in that case, you know, we could just contribute it to libstandard C++ or lib C++.
Could be. I think it does. Ooh, does anybody know before I say something stupid? Yeah, I got like the one comment 600 times. This guy is wrong. I believe it is writer preferring by mandate. Yes, sir.
You didn't mention it, so I guess you didn't try, but still, do you have any numbers how the slim reader writer locks from Windows performs?
From who?
Windows OS.
No, I
tried?
did no testing on Windows. I apologize.
Because it's
I don't have a good
void pointer sized, so it'd be interesting. It obviously doesn't have a mutex backend to it.
Anything else? All right, thank you all very much for your time. Hope you enjoyed.